In node voltage analysis, we use Kirchhoff's current law to find unknown node voltages of a circuit. To define a set of node voltages, we first select a reference node. The node voltages are then defined as the voltages between the remaining nodes and the selected reference node. Let's see it by an example. In this circuit, I use node voltage analysis to find the voltage Vx across the 5 amp current source. First, I define my reference node. I assume this node is my reference ground which has 0 voltage. Then I name the rest of the nodes in my circuit. I name this node A having voltage V1. This node is B with the voltage Vx. Notice that the voltage of this node with reference to ground is the same as the voltage across the current source, which is already named Vx. And I named the last remaining node C having voltage V2. Now except my reference node which has the voltage 0, I have 3 nodes having unknown voltages, and I need to write KCL equations for these 3 nodes to find unknown voltages V1, V2 and Vx. Before starting to write KCL equations, keep in mind that if I have a passive element like a resistor and the voltage across this element is known, by using Ohm's law, I can write the current passing through this element. For example, assume that you have a resistor with the voltage of one terminal V1 and the voltage of another terminal V2. Therefore, the voltage across resistor is V12, which is V1 minus V2. If you remember from the previous videos, I can start from one specific voltage and write KVL to reach another voltage point. So if I assume that the current is passing from V1 to V2, I can start from V1 and write KVL as V1 equals VR plus V2. Therefore, the voltage across resistor is V1 minus V2, and by using Ohm's law, the current passing through the resistor will be V1 minus V2 divided by R. If you assume the current is passing from V2 to V1, then the current passing through the resistor would be V2 minus V1 divided by R. Let's write KCL equation for node A. I assume currents I1, I2, and I3 are leaving the node. By using KCL, the currents leaving the node are equal to the 1 amp current entering the node. I replace I1 with V1 minus 0 divided by 10, replace I2 with V1 minus Vx divided by 20, and replace I3 by V1 minus V2 divided by 50. By assuming current I4 leaving the node, KCL for node B will be I2 plus 5 amps equals I4 plus 1 amps plus minus 2 amps. And by rewriting I2 and I4 in terms of node voltages, we will have this equation. By assuming current I5 leaving node C, I can write KCL equation for node C and finally rewrite currents I3, I4 and I5 in terms of node voltages. Just keep in mind that you can assume any direction for currents. For example, if I assume that current I4 is leaving the node rather than entering the node, it will result in the same KCL equation. Because in this case, when rewriting I4 in terms of node voltages, instead of Vx minus V2 divided by 30, I have to write V2 minus Vx divided by 30, which will result in the same KCL equation. After writing KCL equations for all the nodes, just like the mesh current method, we will have 3 equations for 3 unknown node voltages that can be solved by using Cramer's rule or by using computer software. If you solve these equations by using MATLAB, you will get the voltages for nodes A, B, and C. So the voltage Vx, which is the voltage across the 5 amps current source and equals to the voltage of node B, is found to be 110 volts. In node voltage analysis, it is preferred to have current sources, since we write KCL equations to find unknown variables. There are different ways to handle voltage sources when using the node voltage analysis method. Just like the mesh current method, we can use source transformation to replace the voltage source and its series resistance with an equivalent current source and parallel resistance. For example, in this circuit, I can replace the 5 volts voltage source and a series 2.5 ohm resistor with a 2 amp current source and a parallel 2.5 ohm resistor. Also, I can do the same for another voltage source in series with a resistor and redraw the circuit like this. Instead of 3 parallel resistors, I can replace an equivalent value, assign a reference point, and simply write KCL for this node. If you have a voltage source in your circuit and one terminal is connected to a reference or a known voltage, then the voltage of the other terminal is defined by the voltage source. So there is no need to write KCL for that node. As an example, consider this circuit we checked a few minutes ago. We used source transformation to convert voltage sources to current sources, so the three nodes A, B, and C reduced to one node. Instead of using source transformation, we could also use another approach. I can say that if this node is considered as ground, then voltages of nodes A and C are defined by voltage sources. Therefore, node A is 5 volts and node C is 8 volts. I can find the voltage of node B by writing KCL at this node. Writing KCL for node B results in this simple equation, and by solving this equation, the voltage of node B is found to be 4.07 volts. If the voltage source is connected between two nodes with unknown voltages, then we combine these nodes into a supernode and write KCL for the supernode instead. For example, in this circuit, the currents I2 and IR2 are entering the supernode, and the currents I1 and IR4 are leaving the supernode. Therefore, KCL equation for the supernode will be I2 plus IR2 equals I1 plus IR4. As the final example of this video, let's find unknown voltages V1, V2, and V3 for this circuit. The 2 volts voltage source creates a supernode, and by writing KCL for this supernode, we will reach to this equation. KCL for node V1 results in my second equation, and by using the supernode's voltage source, I can write V2 minus V3 is equal to 2 volts. By solving these equations, unknown voltages V1, V2, and V3 are easily found.